Due to a significant yet unknown malfunction, our spacecraft is effectively lost in space. We lost our control module and all readouts for our data. Lucky for us, the spacecraft uses a standard communication framework that we can tap into. Unlucky for us, it only gives us some very basic data. We'll need to use knowledge of orbital mechanics and physics to calculate various pieces of information about our spacecraft using that data. Perhaps the most important piece of information is where we're going. Today we're going to write some code to calculate and predict our position in an orbit at any time given some simple information. I'm going to go ahead and assume you're familiar with Python and simple vector math. First things first though, let's talk math. The most important equation is this one, Newton's law of universal gravitation. This tells us what our acceleration is at any position due to the pull of gravity. In this equation, mu is called the gravitational parameter. It's a combination of both the mass of the planet and a magic number called the gravitational constant. R is just the distance from the center of the planet. That's all we need. The next equations we need are these, the equations for motion. If you don't already know, the equations for motion are super simple. Our position at any time t is just equal to the velocity times that time t. When our velocity is constant, this function is simple, but if our velocity isn't constant, this function gets a little more complicated. And if our acceleration isn't constant, which our velocity is based off of, it gets even more complicated, or we'd have to calculate multiple complex integrals. Especially in our case, considering our acceleration is dependent on our position. How are we supposed to figure out what our position is if the equation required to find our position needs to know our current position? We don't want this complicated stuff. We want simple. We want enough code to land me on that rock, but enough to do it right. Lucky for us, there's a simple but effective method to solve the problem. Enter Euler. The Euler method basically says that if we know our starting position p at time t, and we want to know what our position is at some short time after that, say t plus 0.1 seconds, all we have to do is multiply our known velocity at t by 0.1 and add that to our current position. We can use the exact same approach to calculate our velocity based on our acceleration at position p. I know this might seem a little confusing at first, but all will become clear. Let's write some code. We need one constant to solve the gravity equation, mu. In order to start solving our orbit, we need to know our starting position and velocity. These are both 3D vectors relative to the planet's reference frame. Let's set our dt to 1 second, and let's do 100,000 iterations. Smaller dt is better, but 1 second is enough for this case. Next, we'll write a function to calculate our following position and velocity given the current one, so just a single time step. First, our acceleration is given by the distance to the center of the planet. We'll write a function to calculate that distance, and then to calculate the vector that points towards the center of the planet, and then to actually figure out what the magnitude of that vector is based on our acceleration. Second, we can calculate our velocity, which is just our current position plus the acceleration we just calculated times our delta t, and we can calculate our position in the same way using our newly calculated velocity. Third, wait, that's it. Wait, that's it? I kind of thought there'd be more to orbital mechanics. Okay, I want to plot this out to make sure it looks right. I'll use the Maya VI library to make a simple 3D plot of the list of positions we just calculated. I'll plot a sphere in there too to show the planet. Alright, finally, let's make a test case. We'll use something that we already know of, the International Space Station. So we can look up a lot of this information that we need. We know Earth's mu value, which is about 3.9 times 10 to the 14th, and its radius, which is about 6 million meters. We know the International Space Station is at an altitude of 408,000 meters, and it's moving about 7,660 meters per second. So everything we need to plot its orbit. And there we go. That's the orbit for the International Space Station. Everything checks out. Orbital mechanics seems like an intimidating topic, but the principles are fairly simple. There are more accurate ways to solve this problem, but this approach gives us a lot of flexibility that we'll need in future episodes, so stay tuned. On the next episode, I'll be tapping into my spacecraft's actual values using the Kerbal Space Program plugin, KRPC, and integrating them into the simulator. Thanks.